Hello, everybody. I know I'm not in today, but we are still going to have fun nonetheless. If you are not at lesson 7 in your workbook, go ahead and get there now. Otherwise, today, let's look at sides and angles of similar polygons. For your first activity, 7-1, all sum none similarity, we're going to choose whether each of the statements is true in all cases, in some cases, or in no cases. Now you won't see these examples in your book. These are just to help you get an idea of what we're doing. Let's take this first statement. Middle schoolers are in 7th grade. Well, middle schoolers are either in 7th or 8th grade, so this would be true in some cases. What about the second statement? Middle schoolers are in 10th grade. What do you think? Some, all, or none? Well, 10th grade is high school, not middle school, so this would be true in no cases. Lastly, middle schoolers are older than 5. What do you think? Well, to be in 7th or 8th grade, you definitely have to be older than 5 years old. So this is true in all cases. Now that you got the hang of it, let's do the ones in your workbook. Before we get to it, let's do a quick review on congruent and similar objects. For two objects to be congruent, they must have the same shape and same size. Basically, they're the exact same object, and we can show this with translations, rotations, and reflections. For objects to be similar, they must have the same shape, but it is okay if they have different sizes, like these triangles below. We can show these with translations, rotations, reflections, and dilations, which will make them bigger or smaller. First one, if two figures are congruent, then they are similar. Do you think this is true in all cases, some cases, or no cases? Let's take a look at these two squares below. These are congruent squares because they match up perfectly. Now if they are congruent, that means that they must also be similar because the angles have to be the same because they're congruent, and the side lengths use the same scale factor of 1 because they're all already the same. So for this statement, if two figures are congruent, in all cases, they will be similar. Let's look at number 2. If two figures are similar, then they are congruent. What do you think? From our last question, we saw that two congruent shapes, like these two rectangles below, are also similar. So these two congruent shapes must be similar and congruent. So sometimes it's true. But what about these two similar shapes? We've taken the small rectangle and dilated it with the scale factor of around 2 to make it twice as big. So these are similar, but we can clearly tell that they are not exactly the same size. So they are not congruent. So in this case, this statement is true in some cases because sometimes similar shapes can be congruent, but not always. Let's move on to number 3. If an angle is dilated with the center of dilation at its vertex, that angle measure may change. Basically, this one is asking if you have a shape and you dilate it using one of its corners. Let's take this shape and dilate it, make it bigger. Will the angle measures change from the original shape? What do you think? Since we know that similar shapes keep the same angle measures when you dilate them, then this will be true in no cases. A dilation will never cause the angles to change. Just to quickly review, similar shapes always have congruent angles. That means when we do a dilation, we know the shapes are going to be similar. All angles are always the same. They also have proportional side lengths. What that means is that the corresponding sides have the same scale factor. So when we multiply a side length by something, it stays even between all the different sides, keeping it the same shape. In your book, make sure you're looking at 7-2, are they similar? You should see two shapes that look like this. I'm going to read what it says below. Priya says these polygons are similar because their side lengths are all the same. Claire says these polygons are not similar because the angles are different. Do you agree with either Priya or Claire? Explain your reasoning. Go ahead and take a second to think about it and write your answer now. So Priya is onto something. These side lengths are the same, 2 and 2, which means the scale factor is even between all the sides. 2 divided by 2 is 1, and that's going to be true for all the sides. But Claire has the winning point here. These angles are definitely different. These boxes represent 90 degrees, and we've got 60, 120, 60, and 120. And just by looking at them, we can tell that they're not the same shape, so these are not similar. Let's look at number 2. You should see these two shapes, and I'm going to read the caption below. Jada says these rectangles are similar because all of the side lengths differ by 2. That is 4 plus 2 is 6, 2 plus 2 is 4, 4 plus 2 is 6, and 2 plus 2 is 4. Lynn says these rectangles are similar. She can dilate AD and BC using a scale factor of 2 and AB and CD using a scale factor of 1.5 to make the rectangles congruent. Then she can translate the line up to the rectangles. Do you agree with either Jada or Lynn, or neither? Explain your reasoning. This is quite an interesting one. We have two different arguments for why these shapes are similar, and they look like they might be with two rectangles here, but let's take a look at one argument at a time. Jada says they're similar because they differ by 2, which is true. 4 plus 2 is 6, 2 plus 2 is 4, but it doesn't matter the difference in the side lengths. What matters is the scale factor. What do we use to multiply by? So since difference has nothing to do with it, Jada's argument is not correct in this case. Let's look at Lynn's argument. Lynn says that we can use a scale factor of 2 for the short sides, and that's true. 2 times 2 is 4, 2 times 2 is 4, and we can use a scale factor of 1.5 for the longer length. 4 times 1.5 is 6, and 4 times 1.5 is 6. Now that's true, we can use those scale factors, but for shapes to be similar, the scale factor has to be the same for all sides. And in this case, we can see, and Lynn acknowledges this herself, if we use these side lengths, 2 and 4, 4 divided by 2, we get a scale factor of 2. And if we use the other side lengths, 6 and 4, 6 divided by 4 is 1.5. These are different scale factors. So we can say that these are not similar. Neither person is right because we have to have the same scale factor for every side. Turn your page and you should see 7-3, find someone similar. Now we're going to actually do a little bit different of an activity than the one described in the book here. In your books, use the space at the bottom of that page, right down here, to recreate this chart. So draw these lines, put number, letter, and explanation. Here you're going to be deciding which shape is similar to the one given, and then you're going to explain how you know. Go ahead and do that now. This isn't in your book, so you're going to have to reference this video while you fill out the chart you made. Match each numbered shape with the lettered shape that is similar to it. Explain how you know that it is similar. Again, you're going to use the chart you made. Here is the shape that you are given. We have side lengths of 6, 8, 6, and 8 with looks like 4 right angles. What do you think is similar to this shape? Figure A or figure B? Make your choice and explain how you know. For starters, it looks like all the angles in all the rectangles are the same. So both shapes check out on that end. Let's take a look at the side lengths. In this first rectangle, we've got a side length of 12 that we're comparing to a side length of 8. That would be 12 divided by 8, or if we write that as a decimal, 1.5. Let's see how the other side lengths check out. 9 over 6. We can write that as a fraction, 9 over 6. And if we check that out, 9 divided by 6, we will also get 1.5, which matches up. So our side lengths are proportional, our angles are the same. That means A is the similar shape. If we looked at B, comparing side lengths of 7 and 8, we can write that as a fraction, 7 over 8. And the other side lengths, 7 over 6, we can already tell that those are not going to be equal. And that's why B is ruled out. Here's number 2. We want to compare this shape and find the similar shape, which is either C or D. Take a second and try it out. Alright, first if we look at the side lengths, 3.5 all the way around, both of these shapes have the same side length too, 9,999 and 4.5, 4.5, 4.5, 4.5. So basically if we use the same scale factor, since all the side lengths are the same, it's going to work out for either of those. So next we need to check the angles. And this one, since all the angles are labeled for us, it makes it kind of easy. We see that we have angles of 60 and 120, but here we have angles of 50 and 130. So we can right away rule out C. Let's check if D checks out. We have side lengths of 120 and 60, which are the same, angle measures of 120 and 60, which are the same angle measures as we have here. With that said, D is going to be our correct choice for number 2. Take a second and try out number 3. Number 3 is kind of interesting in that it looks like our shape is not only dilated, but also rotated. We can see the small side lengths are on the top and the bottom, whereas on E and F, the small side lengths are on the sides. Since these are rectangles, we know the angles are going to check out, since all angles are 90 degrees. So let's take a look at the side lengths. Let's first compare the small side lengths, 3 and 1.5. If we do 3 divided by, or as a fraction, 1.5, that's going to give us an answer of 2. Let's try the long side lengths, 5 over 2.5. 5 over 2.5 is also going to give us 2 through division. These match up, which means that E is similar to the shape given for number 3. Just to make sure, let's try the side lengths of F with our given shape. 6 over 1.5. That's going to give us 4. And trying our long side lengths, 8 over 2.5. That's going to give us 3.2. And we can see that 4 and 3.2 are different scale factors, so that just confirms that F does not work. E is our correct choice for number 3. Let's summarize some of the things we've talked about today. Similar figures have congruent corresponding angles. That is, the angle measures are the same between the two different figures. And they have proportional corresponding side lengths. That means they use the same scale factor for all sides. You might have noticed this, but for some figures like rectangles or squares, we already know the angles are the same. So you can just focus on the side lengths to check the scale factor to see if they are similar. On other shapes that are not rectangles, squares, etc., like rhombuses, it is sufficient to focus on angles, since the side lengths are automatically proportional when you can confirm the angles are the same. Take some time to think about whether or not you accomplished our learning targets for the day. I know the relationships between angle measures and side lengths in similar polygons. That is, you know that angles have to be the same and the side lengths have to be proportional or use the same scale factor. Our second goal, I can use angle measures and side lengths to conclude that two polygons are not similar. Can you look at two shapes and say, oh, the angles are different? That means they're not similar. Or the side lengths have different scale factors. Either of those things you can use to tell that shapes are not similar. It's time for our daily cool down. Head over to joinpd.com and use your class code, and you should see this problem pop up on your screen. Explain how you know these two figures are similar. After you finish up that on Pear Deck, you can use the remaining class time to complete your homework, which is the Lesson 7 practice problems.